Okay, welcome back to another video. Today what we're going to be doing is we're just going to be basically answering questions from the book, from Unit 5. So Unit 5 from the book, and we're going to be doing questions. So if you've got your book handy, what it is the 2014 edition of IB Chem. Oops. We're going to start working through the questions. Just 1, 2, 3, 4, 5. We'll, make this a few-minute video, and then I'll make a new one at another time, and we'll continue on. So if we look at the first question, the first question basically gives you a table, and it talks about specific heat capacity. Specific heat capacity. And the important thing to remember about the specific heat capacity is the units joules per kilogram Kelvin, or we can write that joules kilogram Kelvin. So basically it's how many joules you need to raise 1 kilogram of the material by 1 degree Kelvin. And you could think about Kelvin kind of in degrees Celsius. 1 Kelvin is 1 degree Celsius. But just remember we have to do that conversion because 0 Kelvin is negative 273.5 degree Celsius. So basically it gives you different specific heat capacities. It gives you specific heat capacity of copper. It gives you specific heat capacity of gold, of silver, and finally of platinum. Honestly, all good buys during the coronavirus crisis, right? They're stable at least. And the specific heat capacity is 385. The second one is 234. 234. The third one is 130. And platinum is 134. And the question says you're applying 50 joules of heat to the same quantity of the sample and at the same temperature. So we've got that equation that we can use. We can use the Q equals mc delta T, and then we can calculate the delta T and figure out which one has the biggest temperature change. That's what it wants to know. We want to know the greatest temperature change. So we need Q over mc equals delta T. So basically, mass, specific heat capacity, heat measured in joules, and change in temperature measured in delta K. So what we can see from this, right? It says no matter what, you have the same mass. So we don't need to compare the masses for all of them. So we've got Q over C equals delta T. And then that's all we have to compare, right? We've got the same mass, so we can forget about the mass. It's a constant in this case when we compare all of them. So all we have is Q over C. So Q for all of them is 50, 50, 50, and 50, and C is the specific heat capacity. So we've got 385, we've got 234, we've got 130, and we've got 134, and it's asking which one of these will be the biggest delta T. So remember, delta T, once we took out the mass, was equal to Q over C. So which one of these will be the biggest, right? We've got all 50 at the top for all of them. Then we just look at the number on the bottom. Which one's the smallest number on the bottom? That's this one. So our answer is that gold. Gold. AG has the largest change in temperature. Change in temperature. So that's how we answer those questions. You can either use the formula uh, Q equals mc delta T, or you can just look at these values and say, okay, if I think about the unit is how many joules do I need to raise 1 kilogram by 1 Kelvin? So the smaller amount of joules means that, a 50 joule input will cause a bigger change. This needs 385 joules to raise 1 kilogram by 1 degree Celsius. This only needs 130 joules to raise 1 kilogram by 1 degree Celsius. So you need a lot less energy to cause a temperature change. And that's how we think about these questions, is we can think about it in terms of the equation. If you like math and physics, if you like solving equations, we can think about it in terms of the equations. If not, we can think about it in terms of just logic our way through the question. So number two. So let's write down the information that we have. It says we add 40 joules of energy are added to a sample of water at negative 16 degrees Celsius. So that's equal to what I'd write as TI, temperature initial. And it says it increases to negative 8. So TF is equal to negative 8 degrees Celsius. And it says, what's the mass? We need to know mass. And it says C, it gives it to us, is 2 joules gram Kelvin. So you have to see there's a difference, right? Joules gram, joules kilogram. So they've just been provided in a different way. And we need to know M. So let's look at our formula. We've got Q equals mc delta T. So we need to figure out what our change in temperature is. And our change in temperature is TF minus TI. So delta T equals TF minus TI. So delta T equals TF, which is negative 8 minus negative 16. So our delta T is plus 8 degrees Celsius. We've increased the temperature. So we start to plug in these values. We've got 40 joules equals mass, which we don't know, C, which is 2, and delta T, which is 8. And then we just reposition. We just say, okay, so 40 divided by 2 times 8 is equal to M. And therefore, M is equal to 40 divided by 16, 2.5 grams of H2O. So what I'd like you to do, if you're in my class, and if you're not in my class, that's fine. I always like the final answer boxed in. So I know this happens a lot in math class and a lot in physics class, but it's very important also in chemistry. We just did all of these calculations, and to have your teacher look through and say, okay, like, well, what's going on here? It's nice just to have the correct final answer, because if you have the correct final answer, what we can do is we can the work must have been somewhat correct to arrive at the correct answer. If you got the incorrect answer, then the teacher can look through and say, okay, well, where did they go wrong? Where can I award points? Where can I, award points where you've deserved, where you've done the right work? Okay, so let's keep going down. So we'll do number 3. Number 3 in our textbook. So it gives us, it's going to be the same type of question. You can see what it's telling us. We've got the temperature of a 2-gram sample. So we've got mass, M equals 2 grams. Aluminium increases from 25 to 30. So Ti equals 25 and Tf is equal to 30. How many joules of heat were added? So we need to know Q, and then it says C. C is equal to 0.9 joules gram Kelvin. So the first thing I want you guys to do, I'm going to take this highlighter, is look at the units. The units are very, very important because this is critical to your calculations. So you can see, you look at the units, then you make sure they're all in the same units. Make sure that our delta T is in Kelvin. Make sure our mass is in grams, and our final answer is going to be in joules. So we write down the formula, Q equals mc delta T. So we've got Q, mass is 2 grams, C is 0.9 joules per gram Kelvin, and finally our delta T is TF minus TI. So the final temperature minus the initial temperature, where in this case it equals 5 degrees Celsius, and we can convert delta T is equal to delta K. You know, T isn't equal to K, but delta T is equal to delta K. So this is also 5 degree Kelvin, or 5 Kelvin. So let's do the calculations. So we've got Q is equal to 2 times 0.9 times 5. So Q is equal to 2 times 9 times 5 is 9 joules. And then, like I said, box in your final answer. Take a different color if you have it. 9 joules. And then you're set. So this is how to answer these types of questions. Let's go to number 4 in your book. So number 4 in the book. So it gives us our M. It gives us 20 grams. It gives us the water, the delta T. It says increased by 10 degrees Celsius, which is equal to 10 Kelvin. It wants to know Q. That's our unknown. And C is provided in your data booklet. So it didn't give us C, but in this case we can use C from our from the previous question. In this case, let's see, 4, 2. Okay, so we will have to go to the data booklet actually for this one. So let me just check this really, really quickly. Data booklet right here. Let's try to find that in our data booklet, the specific heat capacity of water, specific heat capacity of water. And we could use, it says it wants our answer in kilojoules. So let's use this number, 4.18. So I'll write that down here, 4.18 kilojoules per kilogram Kelvin. Kilojoules, kilogram Kelvin. So what we have to do is we need to know Q, right? So Q is equal to, and then this is what I said, right? Always look at your units. They want Q to be in kilojoules, so we need to use this one because we need to have final kilojoules. And what we're going to do here, right? We're going to take Q equals, and delta T is fine. So delta T, we can just write 10 in here, 10 Kelvin. We can write in our C value, which is 4.18 kilojoules kilogram Kelvin. That's a lot of K's. And then the problem that we have here is we've got 20 and we've got grams. So to convert 20 grams to kilograms, we have to divide it by 1,000. So we've got 20 and divided by 1,000 to change that into kilograms. So if you look in your data booklet or in your booklet, it doesn't give you a Q value. Although we can calculate a Q value, it wants to know whether your answer is going to be A, B, C, or D. And A is 20 times 10 times 4.18. The second one, we've got 20 times 283 times 4.18. That seems a bit wrong. The third one, we've got 20 times 10 times 4.18. We got all that divided by 1,000. And then we've got the last one, which is 20 times 283 times 4.18 divided by 1,000. So we just need to look, we did the formula. Which one does it relate to? Not 1, not 2, not D. So the answer must be C. So C is our final answer for that one. So yeah, you need to look at the multiple choice. This multiple choice shows us that they don't want the final calculation. They want you to work up to it. So make sure you use that data booklet, right? I'm looking right here at this data booklet, specific heat capacity of water. Make sure you know that this value exists in your data booklet. Okay, so let's work on. I'm just going to check how long this video is, and then we'll keep going. So right now, where does it say? 16 minutes. So we'll do maybe one more question, and then we'll continue on in the next video. So let's look at number 5. So number 5. So this is going to be a little bit of a tougher one. It says use data from section 12. Data from section 12 to calculate the enthalpy change of reaction. To calculate enthalpy change, let's say delta H of reaction for these reactions. So we've got reaction A, which is C2H4 gas plus H2 gas reacts to form C2H6. And we've got B, which, we've got CH4 gas plus H2O gas reacts to form CO gas plus 3H2 gas. So let's look at section 12, right? It tells us use section 12. So although, there might be information in our data booklet, other information for this, we can't use it. We need to use the section that they want us to use. So let's look at section 12. 9, 10, 11, 12. There we go. So we've got the delta H of formation. So we need to use it's providing the delta H of formation. And if you look in your book on page 154, so this is the important one. So in your book on page 154, it tells us 2 different delta H's of reaction. We could figure out delta H of reaction through using bond enthalpies, or we can calculate delta H of reaction through using delta H of formation. And we can't confuse these two. So if we look at section 12, it's delta HF, delta H of formation. So this is the formula we need to use, because the bond enthalpy one, this is what we did in IGCSE. Our delta H is equal to the sum of bonds broken, because remember that was the endothermic part of the process, minus the sum of the bonds formed. So this is where we had to use bond enthalpies and calculate, if we had CH4, we had to calculate the energy between a carbon hydrogen, 4 carbon hydrogens, because we're breaking those to form CO2 as our products. Whereas our delta H of formation, this was a little bit different. This one, this was based on being a state function, which said that no matter how we get there, our delta H's aren't going to change. We can get through there through, like we said, we can walk up the long way up the mountain and get to the top, and the delta H is going to be the same as if we took that gondola to the top and just, skipped all of the hard work to get up there. The delta H doesn't change. So that's the same thing for here. So our equation for that was delta H of reaction is equal to the sum of delta H of formation of the products minus the sum of the delta H of the reactants. So in this case, that's exactly what we have to do. We have to just look at, okay, how much energy does it take to form the products? And this is going to be the thing. Let me just erase this. If it takes more energy to form the products than it takes to form the reactants, it means this reaction is endothermic. If it takes less energy to form the products than it does to form the reactants, then it's exothermic. It takes less energy to form your products, so that means this must also release energy, because you can't have energy gained or lost without without some sort of loss or gain of energy. So let's look at these two reactions. We've got the reaction A. So we need to look up C2H4. We need to look up H2, and we need to look up C2H6. And reaction B, we need to look up CH4, H2O, CO, and H2. So we need to look up the enthalpies of formations of these. And like we said, elements in their standard state, right? Hydrogen is a gas at room temperature. So it's in its standard state, so its enthalpy change of formation is 0. So we can cancel those off already and save ourselves a bit of hardship. But C2H4, let's look at that. So we've got C2H4 ethene right here is plus 52 kilojoules per mole. And C2H6 is minus 84 kilojoules per mole. Then let's look at methane while we're at it. Methane, CH4 is negative 74. H2O, let's see if they've got water here. H2O is negative 285.8, negative 285.8. And carbon monoxide is negative 110.5, negative 110.5. So then we could use those equations that I wrote up top. Delta H of products, which in this case, I'll highlight our products just to save me a bit of time. So that's our product, and carbon monoxide is our product, minus delta H of the reactants. So let's do this. Let's do this. So A of our products is negative 84 minus 52. So A, our final answer, let me see, negative 84 minus 52. Our final answer is going to be negative 136 kilojoules per mole. Let me just look at the book real quick. There we go, just to make sure I've got these reactions right. Make sure I didn't write anything down wrong. Methane, good. Ethane. So negative 84 or 52 for C2H4. C2H4 plus 52, good. And C2H6 is negative 84. C2H6 is negative 84. Good, so negative 84 minus negative 84 minus 52 is negative 136 kilojoules per mole. And let's look at the other one. So we've got delta H of reaction is equal to the sum of delta H of formation of our reactants, which was right up here, of our products, minus our reactants, of our products, minus the sum of the delta H of formation of the reactants. So let's look at this. Let's go down. So we've got delta H is equal to negative 110.5 minus, And the sum of these, so negative 74 plus negative 285.8. So it's minus negative 359.5. So our delta H is equal to 110.5 plus 359.5. We're going to get 249 kilojoules per mole, based on what is in our data booklet right now. So hopefully you got all those values, and join me again for the next video and we'll answer the next few questions.